Okay, this is a little semantic correction video about refraction. Atmospheric refraction. You will realize if you watch my previous videos that atmospheric refraction does not work the way it's supposed to work with their alleged convex earthism, or even flat earthism. It doesn't work that way because refraction will push distant objects downward. And the only way it does work, obviously I showed you how they use a false illegal lift with their convexity in their refraction diagrams, and I showed that in a previous video where you would see less in the distance, not more, if there were refraction at play. And if you were on a surface, on a convex surface or a dish, it wouldn't work like that. And so light is intrinsically bending, and it's bending up toward the center of the Earth. This is the reality that you're inside, the concavity of the Earth. And so what it really is, though, I mean, these diagrams are correct in the way I showed you how refraction really works like that. But it really is just semantics, because what I really just recently noticed as I looked back into it, I realized that it is the less refracted
There's no refraction. It's this
inclination or curvature of the light. Like you'll see two lines here. You'll see the light blue line and the purple line on the left. And I say here, I have it labeled as the refracted trajectory. Well, actually, no. The light blue line is going to be it's like the sweet spot of refracted trajectory within the Earth, because there's a resonant absorptive antenna in the middle. So it's sucking in all the energy. Light is intrinsically bending. It does bend. If you understand anything about Maxwell's equations, I actually showed you how light does actually bend like that. And so there's a natural tendency for sunlight to bend up toward the center of the Earth. But when it bends less, not more, because if you remember a few years ago I talked about radar within the concavity of the Earth, and I showed you how the longer frequency radar is going to show it's not going to bend as much, but you're going to get a greater range in your radar ability. You're going to see, with your radar, you're going to be able to see further when there is a lower frequency. That means it's not bending as much. It's not it's not being refracted as much, and so but when it is higher in frequency, it's going to bend more, and you're not going to see as long. And so that's what's really happening with your long distance shots. When you see the Earth at a distance, you see something along the horizon, a boat in the water, whatever. Under a normal day, it's going to be normally the sweet spot of refraction is going to be fairly high. For all practical purposes, I'll say it's 1.5, So that's what you're normally going to see on a normal day of refraction. But when there's a lower, let's say it's 1.4 on certain days, you're actually going to see further into the distance when there's a lower refraction. That's also working with the sun. The way the sun is viewed toward the horizon with refraction at play, they will say that it's rising in the sky. It's 2 minutes earlier than it should be. Well, that's because of the refraction at play is not going to be bending as much. So there's not going to be as much refraction during that time. Do you understand what I'm talking about? And the way you can really understand how it's falling into place here. Let me find that one video here. Is that this one? It could be this one. This guy uploaded a video, BMLSB69, atmospheric magnification while objects are behind horizon even after zoomed in with P900. And so he goes out and this is the right one I wanted to show. Let's see. Yeah, he goes out and he shoots oil rig platforms at a distance into the water, and I think there's 3 particular oil rigs. One's at approximately 25 miles out, and one's at 20 miles out. I think even the first one's closer. It's closer. I think it's like, I want to say 10 or something like that. And so on different days, you're going to get different levels of the horizon, but also notice too here, pull that down a little bit here, is that when he juxtaposes different days side by side, like on this particular day here, you'll notice on the left is one day and on the right is another day, and there are differences in the horizon level, right? But what he does not bring up, and what nobody really brings up, and I'm bringing it up right now to help you understand why the further you see into the distance, is it going to be less refraction, not more, is because of the actual scale of the objects. You'll see on the left versus on the right, the object on the left within the left versus the object on the left within the right, in scale, it's larger on the left as opposed to the right. Same thing with the other further distant oil platform. It's larger on the left as opposed to the one on the right, meaning that refraction, the lower the refraction, I'll do that in 3D here. The lower the refraction, the smaller the image. And so, let me pull up this in 3D here. I gotta pull up a video window to do that. Let me try display capture. See if that works. Shoot, here. Let me figure this out here. OBS. Come on, OBS. Let me see if I can do this a different way. I'll try a video capture device. No, I'll try window capture. Layout. There we go. Okay. Thank you for bearing with me. Anyway, okay. Back here in Lightwave, I have just a simple test show here. From my top view, if you'll notice on the top left, you see top, and I have it in wireframe mode. Yeah, you can see that. And so there's like two rectangles from the top view, and you see the camera here, that little small dot on the bottom there, toward the bottom. And so it's looking through this glass plane, or plate, or whatever, and there's a little sphere right over there. I'll zoom in real close. You see the sphere over there? That's a purple sphere, and then there's this other rectangular object in the back. And so if I switch to my camera view, you see that over here, like that. So let me switch to VPR, which will give you a natural, kind of rendered-esque version of what we actually see. And so you'll see I have three. Oh, it's not pulling that. Let me pull that one up here so you can see what I'm talking about here. I'll try window capture. Try that one. Okay, let's try that one. There we go. Okay, so what you see here is under the actual surface editors of these different objects, we see a purple sphere, and then there's a glass. It's transparent. I just called it G for glass, transparent, and meaning that you can set the transparency. I have it here at 100, but I also set the refraction to 1.44, and so that glass is actually between the camera and the objects. And so if I change the actual refractive index of the glass, if I get it smaller, you'll see that the image is getting smaller. It's not because I'm moving the camera or anything else. I'm just changing the refraction in the glass. If I make the refraction larger, you're going to see a larger image. Okay, and you also see like the bottom of the gray there. Like if that were to indicate like the horizon, if I was to shrink the refraction, make it lower, that horizon would actually raise up like that. And so also you would see more of the bottom of the orange sphere as I lower the refraction. It gets smaller, but you see more of it. And that's what's really happening with distant objects that we observe in the atmosphere during any particular day when we look at the horizon. It's the reverse. So it's a semantics thing, really. I mean, my videos still make sense with refraction. There's no other way it works with the bending light and the concavity of the Earth, but it's just a matter of inverting your understanding. What the lower the refractive number, the more distance you will see. The shorter those, the smaller those objects will be, but also it will cause you to see more than 180 degrees of the actual stars in the celestial sphere in the center of the Earth. So this all works. It's just a matter of semantics. So the less refraction will allow you to see more into the distance along the terrestrial, whatever you want to say, platform, and as well as the celestial. But it's going to cause that sun to rise the lower than the refractive number. It's the exact opposite what the heliocentrist will tell you. Do you understand what I'm saying? So less refraction. You just have to, I have to reverse title these basically. The purple line on the left would be the less refraction, and the normal trajectory on the right would be a sweet spot of refraction. It would be higher in refraction, and there's going to be fluctuations between, like when we see into the distance, like oil rigs or whatever. There's going to be sometimes they're going to appear to be not, they're going to be offset or like that. They're going to be distorted, and that's because when they're at that lower index of refraction, they're going through different areas of the atmosphere that sometimes increase, sometimes decrease in refraction, but overall they're giving you a lower number in index of refraction than normal, during normal times. Like this guy will tell you that most of the time you're not going to even see the distant oil rigs because there's going to be a higher index of refraction during those times. You understand what I'm telling you? I think he says it somewhere over here. But yeah, that's what it is. Let's see here for 3 months. He went to. He used 3 platforms. Okay. Let me fast forward here a little bit. I think it's mentioned in here, like most of the time you're not going to be able to see the distance here. Almost every day within the 3 months, Grace and Gale was hidden behind the ocean horizon. So that was showing you most of the time you're going to have the refraction is going to be too high. It's the exact opposite of what they tell you. The refraction most of the time is going to be too high into the distant horizon, and therefore it will cause distant objects to be obscured, to be they would be larger than normal. If there was less refraction, they would be smaller. You understand? Okay, I think that really straightens things out and sheds a lot of light to this whole understanding of the shape of the Earth, of how refraction works, and this really this just helps solidify everything. It really won't be long before this information, which will change the entire structure of the world. I'm talking financially, I'm talking, militarily, everything. It's going to change it all. And so that's why it's taken this much time for me to actually come to this understanding of how my Earth really works. And so hang on to your hats. It's going to get really exciting really soon. Okay. So, okay, I actually went in and actually redid this diagram here to help you understand about refraction, what's really happening, and why we see terrestrial objects refracting downward, and why we see celestial objects appearing to refract upward, like the sun or the moon. They will say that the sun rises sometimes due to refraction apparently 2 minutes before it actually does. And what's really happening, as I mentioned before, there's an inversion of orientation to celestial objects. If you hear at the bottom here, your eye is over here, you have 2 lines. You have the light blue line, which is a normal trajectory, and then the purple line, which is a refracted trajectory. I stayed here under greater atmospheric refractive conditions. The refractive trajectory will take slightly longer to rise upward. So the purple one over here. So that's extending your distant horizon. You can see things further into the distance when there is refraction at play. Understand? Allowing the observer to see further, okay, as well as a wider field of view to celestial objects. So that purple line, when refraction is at work, is going to give you a wider view from this point here, obviously all the way to the other side over here. So it's going to give you a wider field of view of the sky. it's going to enlarge your field of view. However, terrestrial objects will bend downward due to refraction, like I mentioned before, while celestial objects will bend upward from our viewpoint. Okay, they're not actually bending the objects in the sky. They're just enhancing your field of view of the sky. So that's why you can see stars. Due to refraction, you can see stars that normally you wouldn't if there was not refraction at play. You understand? So it's widening your sky. That's how the refraction is working. Okay. And also, I mentioned before, these celestial objects are upside down. The moon, the sun. That's why we get the moon illusion, because it's upside down, and it's corrected when you view the moon through your legs. Same with the sun. Same with the stars. Okay, so that's better clarified and a much better drawing to help you understand. So, like I mentioned before in my previous video too, if we're at a higher elevation, whether it's some kind of space vehicle, whether it's over or below the glass at 100 kilometers high, it's going to change the trajectory, and of course it's going to act the same way that refraction does, where it's going to widen your celestial sky. So it's the same kind of effect happening there with that. So that is the reason why. So when a heliotard tries to argue with you about refraction, well, you know that it's proven that objects bend downward, not upward. And the reason why we can see the sun apparently 2 minutes before it rises is because of that refraction is widening. You know, like you open your eyes really wide. So it separates, like this purple line would be the widened horizon. So this distance from here to the sun is wider than from the blue line to the sun. So like if the sun was over here, and let's say it's over here. Under normal conditions, the sun is rising. It's rising. The horizon is splitting the sun in two. But under refracted conditions, it's wider. We have a separation. And that's why they say it rises 2 minutes before. Comprende? Okay. I think you guys get it. When refracted horizon line A, that's over here, and celestial objects are separated. That's the key word. It separates. The horizon is separate. It's separated more from the celestial objects when refraction is at play. That's the key word you need to understand there. There's a separation going on in place, causing them to appear to lift from eyesight. Well, yeah, from your eyesight it appears to lift, even though they would be sinking in this diagram. Well, yeah, it's not really necessarily sinking anywhere. It's just that there's a separation. Let me change that. There. Inversion of orientation. I could spell. Of orientation is due to the bending light that converges at the central octahedral dipole. Okay. So yeah, we have a central octahedral dipole that's converging, that's sucking in all the bending light like that. Okay. I'll put this revised version in the link as well in the description. Okay, there you go.
Alright, I had some quiet time to gather my thoughts, and what I did was I realized that because of the refraction within the concavity of the Earth, as light bends upward and hits the celestial sphere, I told you before in a previous video that it widens, kind of like your eye widens, but at ground level, you're viewing the sun and the moon appear to rise, but they're actually going the other way. There's a compression. That's the key word too, compression. There's a compression that's happening to the celestial sphere. So it's taken the part of the celestial sphere that you normally don't see without refraction, and it's compressing it. So it appears like the celestial objects at the horizon will appear to rise a little bit slightly. But it's all smoke and mirrors, guys. And so after this little clip here, I'm going to show you what I drew on the plane right here. And it's understanding that, because within the 180 field of view at the ground level, you only have 180 degrees to compress more coverage of the celestial sphere. Do you understand what I'm saying? So when the refraction is happening, it's compressing, but you only have 180 degrees to work with from horizon one side to the horizon the other side. You understand what I'm saying? So it's atmospheric refractive compression within the concavity of the Earth with bending light. So refraction will bend objects down, but since that light goes up toward the center and it inverts in orientation, it appears to bend it up. But that's just an illusion. Understand? Okay, watch. Okay, I'm on the airplane right now, and I just had a brilliant idea of why refraction is causing the appearance of the sun to actually lift, but it's not really lifting. If you understand anything about refraction, you watch my previous videos, you'll understand that refraction will actually cause objects to bend downward, not upward. And so this distant sun, when they said the sun is rising 2 minutes before it actually rises because of refraction, on a heliocentric bullshit model is not true. And I explained what's really happening. If you notice here, like, this is kind of crude drawing here, but that's all I have to work with. Your eye is down here inside the concavity of the Earth, and light is bending up. This darker purple line is the refraction line, and then there's a dotted line, which is a normal trajectory line. So the refracted horizon will be higher when it intersects the celestial sphere, like that. Same on the other side as well. So what it's doing, I divided up this very crudely. I divided up the area in which you observe under normal conditions. This line right here to this line right here, that's normal conditions. And so you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sections under normal conditions, but under refracted conditions you get 12 sections because you add these two here. And so because at ground level we only see 180 degrees, that's all we have to work with. You understand? From one side of the horizon to the other side of the horizon. So we have to compress. We have to fit, what did I say here? 12, we have to fit 12 sections into a normally viewed 10 sections, all within 180 degrees. So what that's going to do is it's going to compress the 12 sections into the 180 degree field of view that you actually see them. That's how refraction is working. Okay? Refraction will compress the sky, giving only the illusion of celestial objects, that only the illusion that they're rising. So most of the compression is going to take place at the horizon. So this is it's going to be less affected toward the zenith. So the compression here, this one here, most of the compression is going to be happening toward the horizon. And for the most part, the zenith part of the sky will be pretty much unaffected. But if you actually can actually view with telescopes, I believe, you will see the difference when you're looking at the stars with refraction. There will be a compression, meaning that the gap between the stars will be closing, not widening. That's my theory. Prove me wrong. If I'm wrong, I'll come up with a better understanding of why that's happening. But this is where I'm at right now. There's a compression. Okay, to clarify on the compression that is happening now, it's going to give the illusion that the sun, the celestial objects are rising due to the compression because of the refraction at play. But it doesn't mean they're actually literally rising. They're actually going the other way because of the inversion of the curvature of light. But they're appearing from our eyesight. They're appearing to us. And that's the only way you can explain this. Okay, so the compression, the refraction, the celestial objects are only appearing to rise, but they're not. They have to fit 12 into 10. 12 in a 180 degree area where you normally fit 10, you have to fit 12. And so what it does is it shrinks and especially distorts the angled light hitting the horizon way more so than the actual zenith. Because of the bending of the light operating like that, it's more distorted at the horizon. There you go.